and generating a lot of data up to zettabyte, and then we will be having, so therefore, because of this global explosion, we'll have to have a lot of data stored in the different devices and the computers, etc. So the transmission or the transportation of this data has also to be equally of the larger speed, and therefore this is the starting point of my talk. That becomes so it is very, very complex to handle such type of the data appropriately. And so therefore, we need a proper management to such data, really crucial for the promoting such overloading of the data everywhere across the world. And therefore, the key driver for the explosion are the internet of the things, IoT or cloud computing, artificial intelligence, social media, and digitalization. And therefore, what we futuristic globe will be having, a futuristic globe with the optical fiber, is a concept of representing and managing the global connectivity, digital technology, and high-speed data transmission with the highest level of security. Security becomes very, very important once the data enormously increases, because there is a lot of pilferage, etc., and that can be misleading also. And therefore, there are today what has happened, everything is smart and everything is connected, they say. So therefore, we need a extreme broadband with a massive scale communication and ultra reliable, low latency, highly reliable, upgradable, manageable, sustainable, and cost effective, and plus green communication. Putting all together, we are proceeding from today to the sixth generation of optical network. Before that, I will also be going to the different generation of the optical fiber before coming to the sixth generation. So today's requirement will be, as I already explained to you, that is a low latency, high bandwidth, larger bandwidth connecting everywhere. Battery life is also very important. A reduction in total cost of operation, and has to be green. And therefore, therefore various applications we have already referred, and consumer segments will be across everything, including smart club, agriculture, industry 5.0, and transport, etc. And therefore, what we require is a network which is a robust, green, cost effective, and carrying all the larger band data up to the terabit, petabit, and zettabyte. So global data explosion, as I have already explored, that the 5G to 6G, etc., and all this. So therefore, what we need is a quantum augmented and AI integrated system, which is, because there is a limit to the optical network, or for any transmission network, what you call the Shannon limits. How will really cross the Shannon limit, because we have already reached very near to the Shannon limit. Therefore, the Shannon limit capacity and nonlinear, and therefore, and also once you increase the speed in optical fiber, nonlinearity distortion started playing role. So we cannot go beyond a limit in a normal optical fiber communication. All these things will also be taken care of in the fifth generation and the sixth generation optical network. So today we are reaching up to 400 terabit ceiling under real condition today, but this is not enough. So just see, the year wise, we are reaching starting from the different windows in optical fiber, right, starting from the 850 nanometer to the 1550 nanometer and beyond that. And also we are going to the DWDM, and then also the coherent detection, etc., that will increase our bandwidth. And now this is an important presentation which gives you the first generation. The first generation starts with the PDH and a fiber channel, optical Ethernet, etc., etc. And the data rate which we could reach that time was 140 megabit. The second generation, we introduced the SDH and SONET, and also a concept of ring or automatic protection switches came, and then we reached up to the 2.5 gigabit. In the third generation, this SDH was introduced or connected with the DWDM, and a concept of mesh or automatic protection switches or self-healing also started coming, and we reached up to the 40 to 50 gigabit per second, 50 megabit to 40 gigabit. The next generation or the fourth generation, where the optical transport network or DWDM or ROADM, reconfigurable optical dot multiplexer, was introduced, and the things were reached up to the 100 gigabit. And therefore, how the things were, this was the fourth generation in which we are operating today. And then when we increasing the data up to 1 terabit, we started a concept of EON, what you call the elastic optical network or hybrid optical switches or automatic switches transport network, NFV, SDN, cloud computing, all those things were introduced. And also this slicing of the network, cloudification, orchestration, all these things were introduced in the optical network. And we could reach the data rate up to 1 terabit. So we will go very briefly about these things, which is concept which are introduced, the software-defined network. A software-defined network is a network which is approaching that uses the software to control and manage the all nodes of the network, and that makes the network more flexible and easier to manage. So I'll not go detail of the SDN and FV, but just for the introduction sake, it gives you a better management, better interface, and also a better security because the hardware. But there is a limitation also because the software-defined network is use a central controller. So the maintenance of the controller is become very crucial. So therefore, we have to take care of the things which is very, very important for the single point of the failure presents the potential vulnerability of the software-defined network. And now the network functional virtualization, which is also the cloudification. And this cloudification where every node are not in the hardware form, it is virtualized to move the network from the hardware to software. That makes the operation and the maintenance also the control of the network much easier, and also it reduces the cost and all the heat, etc., and the consumption of the power. It allows service provider run on the server instead of the proprietary hardware. So this is the all benefit of the NFV. Will not go in detail, but there's cost reduction, as I've told you, improved flexibility, improved scalability, reduced vendor lock-in, and also it gives you a very, very simplified network management system to configure and monitor and also to take care of the troubleshooting. Now, the network slicing is a concept which was introduced in the 5th generation of the mobile network that was also introduced over here in the optical network, where is the cutting of one physical network into a multiple virtual network, meaning thereby the whole network is not used as per the services. It is used, the part of the network is only those part of the network are used which is required for that particular service. I'll go a little into that. Each slice is then customized to meet the specific needs of as per the application, services, and the resources. So this is something like that. Allow the slicing for one physical network into a multiple virtual end-to-end network, which is logically isolated. And therefore, you see, after slicing, what happens? The whole network gets sliced virtually, and only those portion of the network comes into operation, which is required for that particular service. And therefore, it gives a simplicity of the network, and also it minimizes the power consumption, and also reduces the cost as a whole. As I told you, before slicing and the after slicing presentation there. These are the things. So therefore, I will not go into detail of all those things, but this is the last one, which is on the top right side. The shared physical network is as per the requirement of as per the application, the whole network is sliced. So we have studied the SDN, NFV, and the slice, orchestration, and cloudification. All things are put. And furthermore, there are a few more things. Energy efficient, which the whole lot have to be made with the energy efficient, meaning thereby we have to introduce few things like elastic optical network, and also hybrid optical switches, automatic switcher optical networks, intelligent optical networks, and ROADM, etc. And then we'll also be using for the energy efficiency the routing and the wavelength assignment, etc., and algorithm, and that will definitely reduce the the energy consumption of the network. That is also our objective of this 5th generation of the network. And then the multi-level traffic engineering will be done. And finally, with the whole cross-layer optimization and the orchestration of the whole network takes place in this 5th generation. And therefore, all those things takes care of the power consumption in the network as a whole, and also make the things much easy and for the communication and infrastructure for the thermal reduction optimization. Elastical optical network, I will not go much in detail, but it is a flexible of the dynamic allocation for the specific. I'll go to, because say this is the grid. Say if this is rather than allocating the whole channel of the DWDM, only those signals are allotted which is required, or the width of the channel is required is allotted, whatever is the required for that particular application. That will be more, and that saves a lot of power if nothing is going, if there no traffic is going and the channel is going, so a lot of space will go unused, and this therefore saves a lot of power by using the elastic optical network. Elastic optical network is just like a elasticity of any rubber, as it is requires as per when you require a lesser bandwidth, it shrinks, but when you require more, it expands automatically. This is one of the more the innovation in the fifth generation network, elastic optical network. This is a depiction of this. So you can see that whenever there is a requirement of more speed, the grid itself expands. The grid itself expands, and therefore and if the requirement is lesser, it shrinks. Therefore, there is a spectral efficiency, and the optical spectrum can be divided up to the flexibility, and the lot of power is saved. It is not as 50 gigahertz as given by the existing fixed ITU grid, ITUT grid. And therefore, sorry, I'll take some water, please. Therefore, the flexible spectrum allocation and the high spectral efficiency, as I told you, and it's called the dynamic bandwidth allocation. Benefit that is scalability, energy efficiency, as they call it, the cost efficiency, as they. Now I'll go to the hybrid optical switches. Hybrid optical switches are both the electronic switches and the optical switches as per the requirement. And therefore, it also saves a lot of power and also cost cuts. I'll also say this is the type of the switching. The space division switching will do, the wave division switching, time division switching. The purely electronic, present situation is purely electronic. And in future, it may be a pure optical, and that will increase the speed of the switching as per the bandwidth of the optical fiber, because the limitation of the optical fiber as a whole is because of the switching. Because optical fiber may have a larger bandwidth, but the total bandwidth output will be as per the switching. The electronic switches are not that fast. Therefore, we require a purely optical switches, but this is by and by. As I told you already, energy efficient. Mostly this is made to the elements. Mostly we are using here is a lithium niobate, but there are the crystal switches also, and also the semiconductor optical amplifier being used, and other things are used in the optical. This is now the high speed optical links. High optical, as I told you earlier, that because we are reaching to very near to the Shannon limit for a single optical fiber, then most important thing is the high capacity is the type of the optical fiber which are using, and in which we have already used a wave division multiplexing. Earlier we used you have the TDM before in the PDH and SDH also. Now each SDH is being used for the different wavelength to generate a DWDM, and now each DWDM is being placed as a subdivision multiplexing, space division multiplexing, and also a polarization, because the light has two polarization orthogonally separated, and so therefore there is no mixing. So what we use a TDM, then DWDM, and before that we use a polarization division multiplexing, and put all on a space division multiplexing to enhance the capacity as whole. And it uses a multi-level modulation format, and therefore by reaching this, the worldwide 2023 we could reach 101.7 terabit, etc. And also, so just I will explain to you. We have the amplitude modulation and the polarization modulation, wavelength, and then this what is called the space modulation, space multiplexing. That's more important. This is the polarization division multiplexing, as I told you. Here also there are the two orthogonal transmitter waves are going, and therefore they are non-mixing to each other. And the data rate they increased by 200 gigabit to 1 terabit. Architecture, as I told you today, is the DWM, and based on which the fiber which you are using, G652, a non-dispersion shifted fiber, and also G655. And the need of there is a need of a new paradigm for the whole communication, and that enhances the quantum, introduces the quantum security and ultra latency and energy efficiency. This how we reach there. I am going to this. So as I told you, the first in 1970 it was megabit, then gigabit, then by fourth generation we reached a terabit, and by 2020 to 2035 we are very near to the 1 petabit, and subsequently by the sixth generation of the photon AI and quantum integrated, we will be reaching, say, 10 Mbps or something like that. Sorry, 10 petabit. And now how the birth of the sixth fiber optic communication, sixth generation takes place. This is the transmission of number one. Everything is done as per the fifth generation, as I told you. Now, over and over, there is an integration of AI to introduce and control and manage various factors in the communication link. And the quantum augmentation is used to introduce a highly secured communication, because when the bandwidth increases, a large bandwidth security is required. And therefore, the sixth generation is the fifth generation plus quantum augmentation plus AI integration. So this is, as I told you, the transmission is a multi-core fiber. Here also this is for the multi-core fiber, multi-dimensional path we use. In the control, it is also the quantum repeater we use. Quantum repeater I will explain later on. And also the quantum entanglement being used, and quantum AI fusion takes place. The target in the fifth generation was the 1 petabit, here the 10 petabit and above. The security was introduced because of the quantum key distribution, QKD, and adaptive quantum communication in the sixth generation. And the example of the fifth generation has already done, say, in the NTT, Japan has done last year 2023 to 1 petabit. And the European Union is quantum net, the introduced of vision for the sixth generation by 2040. India is also doing the work. I will come later on that also. So the fifth generation and the fourth generation comparison is like that. The fifth generation uses the quantum repeater, entanglement amplifiers, and secure. But the fourth generation uses AI-controlled quantum routing and multi-dimensional photonic lattices, and 10 petabit speed is increased. And therefore, now what is the future of the research direction which will go there? Advance in the fiber technology. There is a lot of advancement in the fiber itself. And also the integration of AI and machine learning, quantum communication, and how the space division multiplexing will evolve to meet the demands. We will see like this. Now, the space division multiplexing is something like that. There is a multi-core fiber. Multi-core fiber means one fiber having a number of cores. Not the traditional optical fiber J652 has a single cladding and single core, and also the jacketing. Here, the multi-core fiber in one cladding itself, a number of optical ports are passing through, and that increases the number of the channel, and therefore the whole throughput gets increased. And because the number of cores, and every core is carrying the transmission information, so it uses the special multiplexer and demultiplexer on the other side. So just see like this. This is a optical fiber, which you can see, which we have a single optical fiber, not a single core, but a multi-core, and every core is a channel itself, and therefore it tries to increase and crosses the channel limits by one channel, by one fiber can increase by this. Space multiplexing, as I told you, there are the multi-core fibers are there. Multi-core fibers are there. Multi-core fibers are over there. Number of each core is a channel itself, so it is called the multi-core and multi-channel fibers. And we are using if you are using a multi-mode fiber, then every mode also carries one channel. So we can use a combination of both. We can have a multi-mode and multi-core channel to increase the capacity as a whole. And this depiction of this, the TDM earlier, so we reach up to, say, 1 terabit, and then we introduce a DWDM, and then further we joined the DWDM and the SDM, space division multiplexing, to reach 10 petabit. And this is the conceptual overall transmission, how to increase the transmission capacity by bandwidth into number of the channels, B into N. So this is a concept where the DWDM channel is put to the SDM multiplexer, and SDM amplifiers are used, and also at the end it is demultiplexed, and DWDM gets finally into TDM, and the information carries. So in between, the fiber itself has the capacity has enhanced, right, because of the introduction of SDM, space division multiplexing, which is having a number of cores. So this is also the same thing. we introduce here the improved transmission fibers and also the high spectral efficiency coding, and all these things put together, we finally on the space division multiplexing, we suddenly increase the capacity per bit per second. This is also the modulation, and then we introduce the WDM, and finally when we use the SDM, is tremendously increased from gigabit to terabit to petabit. So this is the same thing as I told you earlier, by how to reach up to the say 10 petabit by space division multiplexing. We also the space division multiplexing, we also call it spatial division multiplexing, because different spaces are being used. So we call it spatial division multiplexing. So don't be confused by the space division multiplexing or spatial division multiplexing. By different notations, we have seen the commercial system and the transmission without SDM and transmission with SDM. I'm going a little faster. This is the depiction where you can see where a large number of the cores is being put in one cladding, and this is very good depiction where there's single mode fiber being converted into a multi-core fibers, and therefore but this is something I'll show you what is the challenges with this. I will let you know. As I told you, multi-core fiber, multi-mode fiber, and hollow core fiber. Hollow core fiber, we don't use any core. We use only air in between, and that traps the, because of the glass, special of the glass, I will come in the latter part. The special glass, the energy gets entrapped in the core itself without following the laws of total internal reflection or refraction. So we have studied the architecture, the multi-core fibers, multi-mode fiber, hollow core fiber, and system which are using a number of, because of there are a number of cores. The transmitter is also multi-core transmitter, and receivers are multi-core fiber. Multiplexer and demultiplexer are especially, it has to be handled very judiciously and very carefully, because if a single line goes away, because there is a number of cores inside, therefore you have to be, the laser has to be very stable as per the thermal also. So these are the certain challenges with the multi-core fibers. So it increases the capacity, increases the high data rate, flexible, and finally improves the bandwidth efficiency, etc. So now, having said all those things, now we've got the new types of the fibers I told you in this SDM, which I have already told to you. The standard fiber as it is in the left side, and the multi-core, multi-mode fiber also having a number of modes, because the core becomes a little wider, so it carries a number multi mode also. So multi-mode and multi-core fibers, and the few mode fiber, because the few mode fiber, if along with that, also takes care of the bending losses. I will come little later part of that. So I'm not going into detail of all those. Multi-core fibers already explained to this. This is a multi-mode fiber, as I told you. The modal dispersion limitation. The distance multimodal dispersion takes because of the multimode dispersion a lot of signal degradation, and therefore mostly this type of the fibers are used for a shorter distance. Hollow core fiber, as I told you, the fiber with a hollow core surrounded by photonic band gap materials. Photonic band gap materials, I will just explain later part. How, because without following the total internal reflection, which is the basic principle of optical fiber, the whole of the energy gets entrapped inside the photonic band gap core. And it is used for the long haul and high performance application. Advantages, reduced losses, etc. These are the depiction of hole assisted. Hole assisted is that there are a number of holes along with the core, and that takes care of hole assisted fibers. Half we call it. It takes care a lot of things of the bending losses. Bending losses, what happens? The leaky mode goes out because of these air holes. It comes back to the core and it takes care of the losses due to the bendings, etc. We also use the photonic crystal fibers and the photonic band gap fiber, as already told to you. The case studies we have done for the case studies applications. The case one, deployment of some major metropolitan cities, and multi-mode fibers used in the data centers, and implementation of hollow core fiber for the long haul transmission with a minimum loss has been studied. And the challenge and limitation, as I told you, because of there is a lot of crosstalk because of the number of cores. You cannot increase the number of cores inside a fiber limitlessly. because there will be a crosstalk from one core to another core, and that also that decides the number of the cores put inside and the limits put on the multi-core fibers. And the cost of deployment is something that's very high, because you have to finally make the splicing of the multi-core fiber with a single core fiber. That becomes very difficult. And much above that, the fabrication of multi-core fiber is very, very complex and costly. So therefore, the compatibility for integration with existing infrastructure fiber architecture is little difficult. Yes, I just told you, because of the number of the cores increasing, and therefore the number gets increased. In summary, the spatial division multiplexing, a groundbreaking technology that refreshes and addresses the challenges of the data-driven, and is already explained earlier also. So this is the whole lot of the SDM optical communications. Here, what we use, we start with the TDM, get converted into DWDM, and also the polarization mode dispersion, and that we put on a SDM node, and along with the ROADM, and finally on the other side, something the same happens, and that increases the whole of the, as you see in the figure, the WDM devices, SDM connected, and SDM optical switches, etc. being used. We also use a add-drop multiplexer, and that to a reconfigurable optical add-drop. We call it ROADM, ROADM. Advantage, they increase the data transmission, reduce the fiber footprint, because the number of the fibers will be much reduced. If you are going to put 10 fibers, we can put 10 core fiber in a single fiber. So that reduces the fiber footprint. The cost efficiency of optical communication, because the whole lot, the optical fiber as it is, the number of the fiber gets reduced. So there will be cost efficiency. Better resource of allocation can be done, and enhanced redundancy. Challenges I have already told to you. I'll not go. Now, what we use also, apart from the TDM and the polarization mode dispersion, fiber polarization mode multiplexing, then we use the DWDM, we use SDM, and we use also a number of bands inside this. Earlier, which we used to use only 1310 and 1550. Now we are going to use a 365 multi-band system, and every band will be going in the TDM, gets converted. In the WDM, and then the number of channel throughput gets increased and multiplied by number of the bands. That we call a multi-band optical networks. The multi-band networks, DWDM, SDM, and finally the capacity. I'm just trying to explain to you how we increase the number of the capacity in a single fiber. This is being studied in IETE, question number 6, study group 15, and also in the question number 2, study group 15. And so I've already told you multiplication of a lot of the carrier. Now, what happens? As I told you, in space division multiplexing, when you're amalgamating it with the DWDM, we call it carrier spatial division multiplexing. So that's I already explained earlier also. But this is the whole lot of the whole things you can see. We are having the space division multiplexing here, and number of TDMs are going to the DWDM. DWDM is going to spatial multiplexing, and finally the fiber itself is the multi-core fiber, and a throughput we can add and drop as per our requirement, and that through a wavelength selective switches. And before going to the spatial multiplex, we go to the multi-gain equalizer and also the forward air corrections, FEC. And finally, because we have to detect a number of channel at the end, we use the electronic MIMO DSP. And the photonic latent spatial multiplex recording. This is explanation of everything which I have already explained earlier. For these purposes, we are using not the silica fiber, but we are using to have two different of the glasses, a very low loss, chalcogranide and telluride glasses for having the low losses. It is ranging say 0.1 to 0.001. So this is also I explained to you along with the core. Along with the core, if we have some holes in the fiber, it will take care of the bending losses. And there will be no bending loss effects, as I have already not gone through the need of the advances of optical materials. I told you. telluride and all those things. It gives also a low loss fiber. And non-linearity also plays a very dominant role in optical fiber. When you increase the speed in the optical fiber, what happens when the number of power is going inside along with each channel, a power ingress inside the core is increased, and therefore there is impinges between the core and cladding interface walls, and a lot of phonons along with the photons are generated, and they interact and create a lot of non-linearity. And these things taken care of in these chloride and telluride glasses. I'll not go to this as I told you, linearity, etc., material flexibility, but there are certain, as I told you, attenuation increases, non-linearity, same thing. No, the data transmission, non-linear topics, and photonic devices. These are the things application in the optical network of these glasses. So now this is the hollow core photonic bandgap fiber, as I told you. There is no core in it. It is the air itself, and because of the lattice, etc., whatever you put inside the core gets back reflected to the core itself. It does not go to the cladding. So we don't need any core material. So whole of the lot gets reduced, and there is a loss because there is no material in between. So therefore, what happens? The losses also gets much reduced in the hollow core photonic bandgap fibers. These I'm telling you the types of the fibers which we use for 1 petabit generation. And then what you using some advanced modulation format, say QPSK, 16-QAM, etc. we are using, or along with the digital signal system processes for the coherent detection, which takes care the amplitude and also the wavelength simultaneously. It is used for the, so having said about the optical fiber itself, now I'll go to the different type of the, introduction of AI and ML capabilities. That will be also a part of the sixth integration. And because of the artificial intelligence and machine language, etc., we are capable of forecasting the traffic and dynamic resource allocation for detection and self-healing and network optimization. I think it's a subject itself. Time may not allow me to go to the detail of, but AI and machine learning for the network optimization, energy efficiency, it is a little. So AI and ML is for the traffic prediction and adaptations are used in sixth generation. A self-optimization and self-healing network. Whenever there is a cut, it tells you where the cut, and it automatic protection switch takes place, and as the self-healing mode goes, and this gives you AI-driven maintenance in the sixth generation networks. This is called the integration of AI and ML with this. The future AI will be used in sixth generation network and also the quantum networks, and it will continue and evolve in innovation itself. Ongoing researches are going on for the signal quality and fault tolerance, etc. How much time is left?
Just 5 minutes more.
5 minutes more. Oh. So I'll just switch to something there, the key photonic integration switches, etc. And I'll go to the little in the quantum integration. These are the same thing because these are the Inferno being Intel is using, Nokia is using. So the quantum photonics, I'll go to because the chip innovation, etc. is also done in the fifth, sixth generation. I'll not go detail. I'll go little in the core principle of the 6G and FO is that it is synergy of the quantum physics and the artificial intelligence that takes place, data light and competition, and also and the quantum technology, where the quantum technology will be using more a superposition and entanglement aspect of the quantum technology to harness the quantum technology, and because this is being used for having a high level of security in the channel. Quantum mechanics is I don't know about detail of that. Quantum mechanics of this, the wave part theory duality, particle sometimes behave like a particle behavior. So quantum state means that can exist a multi-state at one time. You cannot measure both these states simultaneously. there was executed by the Schrodinger cat. You cannot tell the sleeping cat. You cannot tell whether it is dead or alive. So it is stated that it's a very difficult phenomena. It was used by the Schrodinger. So the particles, yeah, can become entangled. Particle entanglement, if that was a spooky action of the distance, I'll not go into detail. I'll just let you know. Imagine you have the two marble. When you spin one marble, another marble automatically spins. And this is called the quantum entanglement of the two particles. When the two particles are generated, it can never break, irrespective of the distance. This is a new concept in the quantum mechanics, which we classical people may not be able to understand easily. But this is the generation. When you spin one marble, another automatically spins the same way. And unless if there is some spin on the receiving side, the receiving side understands that there is a spin of what you call a qubit on the transmitting side. So therefore, you cannot introduce anything in between in the channel, and therefore this is the concept of the quantum entanglement, which gives the highly secured optical network. Because once there is a change in the receiving end, it means there is a change at the transmitting end. If there is a change in the receiving end and the transmitting end has not sent anything, it means there is some interruption, and therefore the security has been compromised. So this is called the quantum entanglement, the concept of quantum entanglement. And also I'll not go detail, there was a spooky action. So the quantum superposition is one, which allowing the particle to exist in the multiple states simultaneously. And therefore, this also gives the sense of security. This is the, you say, in the classical communication, a bit can be either 1 or 0. In the quantum communication, sometimes it remains, the same bit remains 0, sometimes it remains 1. And therefore, it is very difficult to decipher it. And so therefore, the security aspect cannot be compromised at all here. 99.999% secure. Quantum entanglement. So this is the part of this. Utilizing the phenomenon of quantum entanglement enables the sharing of the data between the parties, but they're theoretically immune to intercept the eavesdropping, means there cannot be any interference with the channel itself. And the quantum, I will not go into detail of that. So this is the phenomena which tells you, because the random secret key is sent from encoder to that tape. So the receiver end understands what the encoder has sent, and if there is any change in the message, you will decipher, understand there is definitely some security issue in between. And therefore, this quantum augmentation is being introduced here in the sixth generation. I will not go into detail of that. So these are the various methods. Military, banking, power grid, consumer, medical record, they are using it. So application of quantum communication is mostly in the election security also, because of the electronic voting system. There may be a tampering. So therefore, this quantum communication will be used in the electronic voting system also. So there cannot be some problem, or also the introduction of some mishappening in between the quantum. This is used in the quantum cryptography and quantum teleportation. This will allow scalability, structure, encryption. There's no cloning theorem is also very important in the quantum communication, because system states are nearly impossible to create the identical copy, and therefore of an unknown quantum state. So you cannot create a quantum state which is not known. So this is called the encryption by no cloning theorem. This no cloning theorem gives the highest level of security in the optical communication. The quantum augmentation fundamental, I now go to increase of this. And this is the QKD, and this also the architecture of this, the sixth generation fiber optic communication will be a multi-core, multi-mode fibers, quantum routers and controllers, real-time photonic signal optimizations. And network intelligence layer has also been introduced. The AI manages the spectral allocation, predictive and autonomous representation. And integration with the quantum computers, they told you earlier, the foundation of the quantum internet is the basis of the security. The main objective of using the quantum aspect in the communication is to increase the security aspect. Energy efficiency also zero, because we are using a zero quantum amplifier. It's a very good concept. I will take about a minute. Quantum, mostly in the amplifier, what happens, unless you put some energy, no signal can be amplified. But here, and this is the quantum, you don't need any energy to be input for increasing. So therefore, these quantum amplifiers are almost zero energy. So this is also one of the a groundbreaking advancement in quantum-based optical, 6th generation optical amplifiers. So these are the integrated photonic processors are being used. Cryogenic photonic perform multidimensional. I will not go in detail. AI, as I told you, the optical layer are introduced. So this is the optical layer intelligence being used. A zero energy quantum amplifier, as I told you, a near zero energy quantum amplifier, as I told you earlier. This is the concept which is different bands are being used, OESCLU, and they are being put to the gain equalizer, and they're put to the number of multiplexer, the time zero multiplexer, DWDM, and then SDM, and then finally put to the optical fiber. And here, the recent laboratory announcement that was explained this over figure in March 2024 in San Diego, California. It was introduced, and the total bandwidth capacity which could be achieved was 402.2 terabit. So these are the different channels which are using. They are using very good. And this is the milestone of only 2-3 minutes more. 1 terabit demo is 15 done, and 400 terabit commercial, and 1.02 petabit entity has been produced. A quantum classical integrated network is expected to be 2035. A recent laboratory achievement, the entity, as I told you, 1.02 petabit over a 51.7 kilometer was achieved by Nokia Bell, also 1.4 petabit. Prototype was done. KDD and the European Union Quantum Net Collaboration has done some more experiments on this. And the field trial of the global researchers of the USA, Japan, European Union pilot projects, quantum repeaters are being used, multi-core fibers are being used. And expected timeline, like the quantum safe pilot will be by 2535, or AI integrated 6th generation course will be generated by 2035 to 2045, and commercial 10-bit system will be in place by 2050. And performance benchmark will be having a capacity more than 1 petabit. Latency will be increasing, say, 1 microsecond to 0.1 millisecond. And also the energy will be less than 1 PJ per bit, and security quantum, unbreakable quantum security will be there. And the 5th generation, this is all told to you. This is called the quantonomic networks. Quantonomic networks will also be used. The quantum internet will be used. And the 60 metaverse, and I'll not go to detail of it. These are the space which will be used, the 6th generation quantum networks. And the healthcare also, the remote surgery robotics will be used for 6th generation networks. And India's digital future by 2040 also. The BharatNet quantum backbone will be by the 2040. Indigenous photonic chip fabrication will be done by 2040 when there will be and then the quantum startup by R&D hub, etc. Standardization of the policy will also take place, the global interoperability and the quantum spectrum regulation and security framework, etc. The open research equity. So there's certain question which we are being dealt with different universities, and also this, which is the quantum error correction codes is one of the things which is to be taken care of, and also how to put the how to trust the artificial intelligence for the it is correctness and the transparency, scalable entanglement of the quantum are also be taken. India's strategic, the C.ISRO, IIT's collaboration being taken. Leadership in the 6th generation fiber optic and the quantum network intelligence. And our global vision is a fully quantum integrated network, light as an intelligent formation carrier, and photon-based computing, a single photon-based computing convergence, single photon. And so the conclusion is that the 6G fiber optic communication merges with AI and quantum and photonics. The 6G merges AI, means quantum augmentation, artificial intelligence integration, and laid on photonics. And then we'll be having some circuit beyond 1 petabit towards the 10 petabit intelligent optical highway. So that is why. Thank you very much.
Thank you. Yes, Kamakshi.
Thank you so much, sir, for this enlightening session.
Question answer session.
Yes.
Open. If anybody wants to ask any question, welcome.
Dr. Anuj, I have one question.
I am sure. How are you?
Are you able to hear my voice?
Yeah, I can. Yeah, please.
What is there any cost comparison about the our present optic fiber cable and the new cable what you are telling? What is the cost comparison? How costly it is?
Effectively, it is cheaper. The new one is cheaper because in our fiber, a single core is going on, and therefore the carrying capacity is singleton. Though
Yeah.
there is a manufacturing cost is much higher than the single core, but because it is carrying a number of core, although the channel information is much more, then effectively it becomes cheaper in the long run.
Okay, okay, that is good. Yes, thank you.
Anybody else? Yes, Kamakshi, you proceed with the vote of thanks.
Sure, sir. So I would now request Mr. Rahul Khatri, Operations Manager at CPM India in Delhi, to give the vote of thanks. Before that, I would like to introduce Mr. Khatri. Mr. Rahul Khatri has done his MBA from NMIMS Mumbai. He's also an electrical engineer by profession. And he has a diverse career, right from being an RJ at Red FM to product management at Vodafone Idea. And currently, he's serving as an operations manager at CPM India in Delhi. So over to you, Mr. Khatri.
Thank you, Kamakshi. I hope I'm audible.
Yeah,
Yes.
Thank you, everyone. I would like to start my thank you note with the speed of light is constant, but the speed of innovation that depends on us. What an inspiring session we have had today. On behalf of the IoT Society of India, I would like to extend a heartfelt thanks to Dr. Anuj Kumar Srivastava for an absolutely insightful, forward-looking, and a great session on sixth generation optical fiber communication with quantum augmentation. Dr. Srivastava, your deep expertise and futuristic vision on how quantum technology can transform fiber communication truly energizes us all. We we have given you have given us a lot to think about and even more to look forward to in shaping India's digital future. A big thank you to the organizing team and technical group for making today's session possible and seamless. To every participant who has joined us on YouTube and Zoom, your enthusiasm keeps these conversations meaningful and alive. Special thanks to to Shri Puneet Pandey, Secretary IoT Society of India, Lucknow chapter, for providing a technical support in organizing this webinar. As we conclude, let's keep the spirit of innovation alive, transforming ideas into actions and challenges into opportunities. The digital journey of quantum enablement, high-speed digital India has begun, and together we'll lead it forward. Thank you once again, and we look forward to all of you joining more such sessions in the future. Thank you, everyone.
Thank you.
Thank you so much.
thank you. I think with the permission, I think President has not joined yet. We close this session. Wonderful session by Dr. Anuj Kumar Srivastava. And we have to have more sessions in future from Dr. Srivastava. Thank you, Dr. Srivastava.
Thank you.